This is Lab 4, which deals with spring mass motion. The objective was to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. I made a computational model that analyzes this motion, and I compared the predicted and observed motion of the mass. Here's the main result for my computational model. This is the video that I analyzed in Tracker, and as we'll see later, the computational model matches up very nicely to this video. My initial conditions, the mass was given to me. The initial position I extracted from my Tracker data, and the initial velocity is 0, and the weight force is 9.8 meters per second squared. I calculated the average time between oscillations to equal 1.504 seconds, which equals the period of oscillation. By finding the period of oscillation, we can then find stiffness by rearranging the formula to equal 4 pi squared times n divided by t squared, and we get the stiffness to be 7.016. We can then put that into a formula to find L naught, which we find to be 0.138 meters, and the L was given to us as 0.70 meters. Here's the beginning of the code where we implement the initial conditions. We have the gravitational force to be 9.8 meters per second squared. We have our spring constant that we calculated earlier, our L naught. We find L, which is ball dot pos minus spring dot pos. L hat, we have to have the unit vector in order to compute the spring force. And then for S, we have the magnitude of L minus L naught. And here we compute the system energies. So K equals 1/2 times mv squared. So ball dot m times the magnitude of ball dot v squared. The gravitational potential energy of the spring mass system is mass times g times position, and the spring potential energy of the spring mass system is 1/2 times the spring constant, Ks times s squared. For the first part of the calculation loop, we'll be implementing Newton's second law, where we find the final velocity and the final position of each iteration of the code. And we also have F gravity, which is negative mg, and F spring, which is negative ks of s. We also have F net, which is all of the forces added together. So here it is represented in the code. For the next part of the code, we'll be implementing the energy principle, and our system is the mass and the spring and the earth. So that gives us delta E equals delta K, the kinetic energy, plus delta U, the potential energy of the gravitational force, and delta US, which is the potential energy of the spring. All of this equals 0 because there's no energy transfer to or from the surroundings with this system. Here it is implemented into the code. We will calculate the energy changes by having K, delta K, UG, delta UG, US, and delta US, which will be implemented into our graph plot. Here's the result when you run the code, and you can tell that it compares nicely with the video because the spring kind of changes direction as it moves along, and it creates this kind of interesting little interlacing pattern. What does it mean? For your model system, is the energy principle satisfied? Yes, it is, because we concluded earlier that delta E would equal 0, and this yellow line represents delta E, which is the total of all of the energies added together. The blue line equals the kinetic energy. The green line is the gravity potential energy, and the red line is the spring potential energy. Using the data obtained in Tracker, make two separate estimates of oscillation periods. In order to find the period of oscillation, which equals t, I took the average time in between each oscillation. For the x, I subtracted the time from the tip of this slope minus the time from the tip of this slope in order to get 8.262 seconds, and there's 5 iterances in between these, so you divide that by 5 in order to get 1.652 seconds. For the y, I did the same thing from the top of each slope. So there's 6 periods of oscillation in between here, and I took the top of the last one subtracted by the first one, and which equals 9.022 seconds, and divided that by 6 in order to get the period of oscillation to equal 1.504 s.